In this next video in the Geometric Algebra series, what I'd like to do is cover a few topics that may be of interest, especially to game developers and programmers, those who are especially interested in some of the specialized computational aspects of doing things like rotations and interpolations. We have three topics on the agenda for today. Firstly, we have linear interpolation, or Lerp. This will be relatively simple. Secondly, we have what's going to encompass the majority of the work in this video, which is going to be spherical interpolation, also called SLERP. Lastly, we have normalized linear interpolation, or normalized Lerp, also called NLERP. Let's tackle linear interpolation first. What I'm interested in doing here is, given two vectors, a starting vector and a final vector, is to interpolate along the line joining the tips of the two vectors to form these intermediate vectors, the interpolated vectors. Let me draw this out. So let's say I'm given some starting vector, perhaps some initial vector, which I'm going to call v sub I, my starting vector, and a destination vector, a final vector, which I'm going to call v sub f, my final vector. What I'd like to do is interpolate, moving from vi to vf along the line joining the tips of these two vectors. Now, the vector going from here to here, if this is vi and this is vf, the vector going from here to the tip of vf, this is simply vf minus vi. And hopefully you can see that. If I add vi to vf minus vi, I simply get vf. So I'm interested in interpolating along this line joining the tips of the two vectors to form a vector, let's say, intermediate along that line. Let's say right there. I'm going to call this vector, this interpolated vector, v sub s, where s is going to be some parameter which I'm going to allow to range between 0 and 1, depending on where along this line joining the tips of the vectors I'd like to be with this vector. To find what this vs is relatively simple. What I'm going to do is take vf minus vi, scale it down by multiplying by that parameter s. So the vector from here to here, let me draw that right there, is simply going to be s times vf minus vi. Where, again, s is going to be some parameter which I'm going to allow to range between 0 and 1. Now, to get vs, I simply do the vector sum of vi plus s times vf minus vi. So let me write that. Vs is equal to, starting out at vi, that initial vector, add to it s times the difference, vf minus vi. Now, simply distribute that s to both terms. I have vi plus s times vf minus s times vi. Now combine this term and this term to get 1 minus s times vi plus s times vf. That's equal to v sub s. And that right there is simply the formula for doing a linear interpolation. Again, I was saying that I'm allowing s to range between 0 and 1. Suppose s is equal to 0. Plugging in this formula, vs is simply equal to vi. That's when you haven't moved from vi at all. If s is equal to 1, notice in this formula, first term goes away, 1 minus 1 is 0, and I'm left with vs being equal to vf. So you've moved all the way along to vf. And of course, we're interested in the interpolated values, so normally what you're going to do is let s be something like 0.5, which is to say you're midway between vi and vf along that line joining the tips of the two vectors. And you can see that what vs is going to be in this case is going to be 1/2 vi plus 1/2 vf. And you can see what this formula is doing is giving the correct linear combination of vi and vf to get the proper interpolated vector. And to be extra clear about what all this stuff looks like, the linear interpolation, let's let s be something like almost 1, let's say 0.9, in which case vs, where s is equal to 0.9, this is going to be, well, 1 minus 0.9, that's going to be 0.1 times vi plus 0.9 times VF. And on your diagram, this would approximately look something like this, where VS is going to start out, again, from this location here. It's going to go right there, where it's about 90% of the way from VI all the way over to VF. So this is this location here, about 90% of the way. It looks something like this. And of course, if you were maybe 50% of the way, the vector would be approximately there, that interpolated vector. That's where S is 0.5. So you can see what this is allowing you to do is, you can imagine having like an animation where S is allowed to take on different values. And this interpolated vector slides from where S is equal to 0, starting out of VI, along this line toward S equals 1, where you finally reach VF. And it goes through all these intermediate vectors, these interpolated vectors, when S is between 0 and 1. Of course, S need not range in the abstract between 0 and 1. If it were outside of 0 and 1, you would simply interpolate along the extended line. If you just take this line and extend it, for example. Let's extend in this direction. Now the vector from here to here might correspond to something like S taking on the value of minus 0.5, something like that. And if you allow it to range above 1, let's say over there, the vector from here to here, that might correspond to a value like S equals 1.2. The last thing I'll point out before we're done with the linear interpolation part of the video is the particular sort of linear combination of VI and VF we see showing up in this formula. Take a look at the two coefficients, the 1 minus S and S. Notice the sum of those two, 1 minus S plus S, that's simply equal to 1. Now, such a linear combination of vectors where the sum of the coefficients in that linear combination is equal to 1, such a combination is what's called in geometry an affine combination. And you can see why these affine combinations might be important, because they allow for the extension of the line joining the points, 2 points, or in this case, the tips of two vectors. Let's move right along to our second topic in this video, which is going to be spherical interpolation, or the acronym SLERP. What I'm interested in doing here is something analogous to what I was doing in linear interpolation. That is, given two vectors, an initial vector, which again I'm going to call VI, and a final vector of VF, I'm interested in finding those interpolated vectors in between VI and VF. In linear interpolation, what I mean by in between is along the lines joining the tips. Now in spherical interpolation, what we're going to do is find those interpolated vectors along an arc joining VI and VF. This, of course, being a geometric algebra video, we're going to use some of the tools of geometric algebra to solve this problem. Let's now draw out what exactly we're looking to do here. Let's consider a unit sphere. So everything in sight is going to be of length 1. So every vector you see now in this spherical interpolation part is going to be of unit length. So let me draw out the starting vector. It's going to touch the surface of the unit sphere, being length 1. Again, I'll call that VI. That's my initial vector. And I have a final vector toward which I'd like to interpolate. Let me call that VF. And instead of interpolating along a line, what I'm going to do is interpolate along an arc, joining VI to VF. So it's going to look something like this. But it's not just any old arc moving from VI to VF. It's actually going to be the arc formed by considering the plane VI wedge VF. So imagine forming that bivector, completing that parallelogram, and extending this plane out in the direction. Now, if you consider the way that this plane of VI wedge VF cuts or intersects this unit sphere, it's actually going to intersect it in a circle, namely a great circle of the unit sphere. And you can imagine that just extending this arc all the way around the sphere. Now, what's interesting to note about these great circles, the great circles, by the way, they have their centers coincident with the center of the unit sphere. What's interesting to note about these great circles is that they're what's called the geodesics of the unit sphere. A geodesic being, if you have a surface, the shortest path joining 2 points on that surface. So these arcs, which would be segments of the great circles would be the geodesics of the unit sphere. So we're interested in interpolating along these great circles from VI over to VF. For example, an interpolated vector might look something like this. And again, I'm going to call those interpolated vectors VS's, where the S is going to be, again, some parameter. Initially, I'm going to allow it to range only from 0 to 1. Again, S equals 0 corresponding to when you just start out at VI. And S equals 1, meaning you've moved all the way along over to VF. And those intermediate values being somewhere in between along that great circle. Now, what's nice in this problem is that, remember how we started out here, we considered the plane of VI wedge VF. So all of these interpolated vectors are going to also be on that plane, which means that they're going to be just some linear combination of VI and of VF. And our goal is to find the right linear combination to use. Now, since all of these interpolated vectors, the VS's, are going to be on this plane, on this 2D subspace of 3D, we can use what we know about rotating in 2 dimensions. Just in this particular case of taking a particular 2-dimensional subspace out. So I'm going to enlarge this picture here. Again, we have VI, my initial vector, and I have a, let's put VF over there. And we have the arc associated with that segment of the great circle. And we have our interpolated vectors. For example, one such interpolated vector might be right there. Vs, where again, S is some parameter. Now, Vi is going to make some angle with Vf. Let me call that angle from there to there. Just call that theta. Now, Vs is going to be some proportion of that full angle theta. So the proportion, the angle from Vi over to Vs, is going to be this angle right here, which I'll mark doubly. That angle is just going to be that parameter S times theta. So again, if S were to take on the value of 0, Vs would be just the same thing as Vi. If S were to take on the value of 1, Vs would just be the same thing as Vf. So this is just a picture corresponding to the particular 2D subspace that we're interested in. As I was saying over here, Vs being on this plane defined by Vi wedge Vf is just going to be some linear combination of Vi and of Vf. And our goal is to find the correct one to use, given some value of S, given some value of that parameter. So let me write that out over here. So Vs is going to be some linear combination of Vi and of Vf. Now I'm going to call those two coefficients alpha sub s and beta sub s. Now, of course, these coefficients are going to be functions of the parameter s, because the right linear combination to use is going to, of course, depend on where along this segment of the great circle you want to be. For example, if you want to be midway in between, those coefficients are going to be different than the right coefficients to use if you want to be 75% of the way along the great circle, the arc of the great circle. Now it's finally time to bring in some geometric algebra, what we've learned to do with both 2D and 3D rotations. What we learned about 2D rotations is actually going to almost suffice for this video, because we're only considering a 2D subspace here. Now, Vf is a rotated version of Vi. It's just Vi operated upon by some rotor to move it from Vi over to Vf. So actually what I'm going to do here is I'm going to note that Vf is just equal to Vi times a rotor acting on the right times Vi. Now notice, because it's a 2D subspace, I'm allowed to do rotations in this one-sided fashion. Remember, in general, you want to think of rotations as being done by a two-sided operation, where you have a rotor and its dagger, its conjugate rotor, on the other side. But here, because we're working in a 2D subspace, I'm allowed to just consider a one-sided operation. That'll be perfectly fine. Now, what this rotor R is, remember, these are tied in very intimately with exponentials. So this rotor R that moves Vi over to Vf is simply going to be e to the theta, where that's that theta, times b hat, where b hat is going to be the unit bivector in the plane of vi wedge vf. So you can just think of that bivector vi wedge vf, which I drew out over here, just normalized, divided down by its magnitude just to make it of unit area. So that's all that really is over here. A couple of things I'd like to point out about the algebra of this rotor here. Now, vi times r, I claim, is just the same thing as r dagger times vi, where r dagger, remember I was saying in the video on rotors that this dagger is more or less the conjugate. Taking the conjugate of this is just going to be e to the minus theta times b. So vi times e to the theta b hat is the same thing as e to the minus theta b hat times vi. And this should be quite familiar if you have some experience with doing rotations using these exponentials. So these are actually the same thing. This is something we're going to use in our derivation where we try to find the right linear combination to use. That if I want to swap the order of vi and r, I can do so. I just have to include that conjugate or the dagger in that rotor. If you've forgotten why I can do this algebraically, what I encourage you to do is just expand this stuff out. Expand out vi times e to the theta times b hat using Euler's formula. And remember that if you have a geometric product between a vector and a bivector, and if that vector is in the same plane as the bivector, they will anti-commute. That's what introduces a minus sign, and why this is equal to this, having to add in that dagger rotor. Now, what I'd also like to observe here, and what's going on, is that Vs is also a rotated version of Vi, again being operated upon by a rotor. So Vs is going to be equal to Vi times, again on the right, it's going to be E not to the theta times B hat, but just S theta times B hat. Now what's very tempting to do is just write this in the following way. Vi times E to the theta B hat to the S power, which is exactly what I'm going to do. And this e to the theta times b hat was just equal to r. So I can really write Vs as Vi times r to the S power. So this is being operated upon not by the full rotor, but the rotor to the S power. So let me write this over here. So we have r to the S power is equal to e to the S theta b hat. And just like r has a dagger rotor, this also has a dagger rotor, which is just going to be the conjugate. So r to the S dagger is equal to e to the minus S theta b hat. And for similar reasons up here, I say that Vi times r to the S is equal to r to the S dagger times Vi. So again, if you want to swap the order, with a special condition that these vectors are in the same plane as b hat, which they indeed are, you have to add a dagger over there if you want to make this a left-sided operation. There are a couple other things I'd like to remind you of concerning the algebra of these rotors. One is just something pretty obvious, that if you have a rotor and you take the dagger twice, this is just the same thing as the rotor itself. Similar to in complex numbers, if you take two conjugates, that's equal to doing nothing. The second thing I'd like to remind you of, let me move up here, is if I have two rotors, let's say R1 times R2, where the times is, of course, the geometric product, take the dagger of that, I say that this is equal to R2 dagger times R1 dagger. Let me show you why that is. So let's say, again, the rotors are just geometric products of unit vectors. Let's say R1 is equal to the product of two vectors, AB. R2 is just a product CD. A, B, C, and D are just any old unit vectors. R1 times R2 is going to be A, B, C, D. Take the dagger of that. The dagger just means write this in reverse order. So instead of A, B, C, D, it's going to be D, C, B, A. So we have D, C, B, A. What's DC? That's just the reversed R2, which is just R2 dagger. What's BA? That's reverse of R1. And there you go. So this is very similar to probably something you've seen if you've done matrix algebra, where if you have the product of matrices and you want to do something like take the transpose, what you have to do is make sure to swap the order when you additionally add in the transpose operator. That is, if you had two matrices A, B, take the transpose, this is equal to B transpose, A transpose. So with some of this stuff in mind, let me go back to this linear combination of VI and a VF here, with the two coefficients being alpha sub s and beta sub s. I was saying that V sub s is equal to VI times R raised to the s power. That's equal to alpha sub s times VI plus beta sub s. VF, remember that's VI times R. So this is the equation I'd like to work a bit with. Remember, what we're trying to do is find the right coefficients, the alpha sub s and beta sub s. So let me clean this up a little bit. So I've erased a few things and just moved this new equation up to the top here. What I'd like to first focus on is solving for alpha sub s to find that right first coefficient in front of VI. The problem is I have this other unknown here, but I'm going to use one very nice property of the wedge product, which you'll remember that if I take a vector wedged with itself, that's equal to 0. Now this thing here, VI times R, is just some vector here, namely VF. So what I'm going to do is actually wedge both sides of the equation with VI times R. So wedge both sides on the right by VI times R. And you'll remember too that the wedge product between two vectors, let's say U wedge V, is equal to 1/2 UV minus VU, where this multiplication here and here is just the geometric product. So I'm going to use that feature of the wedge product. On the left-hand side, what I have is, just writing this out, it's going to be 1/2 VI R to the S times VI R minus VI R times VI R to the S. And on the other side, I have 1/2. I don't have to consider this first term here, because this is going to wedge out. So this is going to be 1/2 alpha sub s. This is going to be VI times VI R, or VI squared R, minus VI R VI. Looks pretty complicated, but it's actually going to simplify once we use those algebraic properties. Let me get rid of those 1/2s on both sides. The first algebraic property I'm going to do here is I'm going to swap VI and R to the S power. Now remember, when I swap the order of those two, I just have to add the dagger in there. So this first term is actually equal to VI squared R to the S dagger times R minus, I'm going to do the same thing with respect to VI and R over here. And I'm going to get VI squared R dagger R to the S. And I'll do that once more with this term over here with respect to VI and R. So I have this is equal to alpha sub s times VI squared R minus VI squared R dagger. Now remember that the square of a vector with a geometric product is just equal to its length squared. And everything inside here was of unit length, so these VI squareds, those are just 1. So let me rewrite this line here with that in mind. So I have R to the S dagger times R minus r dagger r to the s equals alpha sub s r minus r dagger. So this simplifies very nicely. One additional thing I'm going to do is take note that this thing here, r dagger times r to the s, is actually the dagger of this whole thing. Let me rewrite the left-hand side just to make that clear. R to the s dagger times r is equal to the dagger of this. R to the s dagger times r, all dagger. And just to make sure this makes sense, remember when you have a product here of rotors and you have the dagger. So if you swap the order of the rotors and add the dagger to each one, remembering that the double dagger is just equal to nothing, really, you'll see that that's indeed equal to this term over here. So I've rewritten the left-hand side as that, and then I'll just keep the right-hand side over here. Alpha times s, alpha sub s times r minus r dagger. Now, we have a rotor minus its conjugate, and we're going to discover something very similar happening to when you have a complex number and you subtract away its conjugate, in that the imaginary part is going to be the only thing left. It's actually going to be twice the imaginary part of all this stuff. Let me make that clear. Let's consider what r minus r dagger is. So r minus r dagger is going to be e to the theta times b hat minus e to the minus theta times b hat. Let's use Euler's formula. First term is equal to cosine theta plus, it's going to be sine theta times b hat. And just a reminder, you can use Euler's formula because b hat will square to minus 1. Now we're going to subtract away cosine theta minus sine theta b hat. And notice what's going to happen here. This term is going to cancel with that one. And I have sine theta times b hat minus sine theta b hat, which is simply 2 times sine theta b hat. So let me add that to the right-hand side here. So this is actually going to be 2 times alpha sub s sine theta times b hat. Now, formally, we have something very similar going on the left-hand side. We have a rotor minus its dagger. So we're actually going to get something very similar to what we've just got out here on the right-hand side. Let's just consider what this product here is, what r to the s dagger times r is. So that's going to be r to the s dagger. Remember, that was e to the minus because it's the dagger, s theta b hat times, now r was just theta times b hat. So just taking the product of those exponentials, that's going to be e to the 1 minus s theta times b hat. Now, what the left-hand side here is saying that I have to take this thing, subtract away its conjugate. Now, that's exactly the same as what I've got up here, except instead of a theta out front, I have a 1 minus s times theta. So it's going to be exactly the same thing over here. So what I'm going to actually get on the left-hand side is 2 times sine, not of theta, remember, just a slightly different argument in front. It's actually going to be 1 minus s times theta. And again, times that unit bivector in the V1 wedge VF plane. Now let me cancel out those 2's. Now we've got two bivectors equal to one another. If two bivectors equal, certainly the coefficients on front have got to be the same thing. So that means that sine of 1 minus s times theta is the same thing as alpha sub s times sine theta. So what that means is that, just doing the last manipulation there, that alpha sub s, just dividing both sides by sine theta, is equal to sine of 1 minus s times theta divided by sine theta. So we've got our formula as a function of s of that first coefficient there, the coefficient that's going to have to be in front of vi, the starting vector. So where halfway done. There's our coefficient, alpha sub s. We're going to do the same trick using the wedge product just to solve for the second coefficient, the beta sub s. Now, what I'm going to do is to get rid of this first term, I'm going to wedge on the left by vi. That'll get rid of this first term. So I'm going to wedge on the left by vi. So vi wedge the left-hand side is equal to vi wedge the right-hand side. So I have, again, using this formula, that the wedge product is equal to 1/2 uv minus vu, where u and v are the vectors that you're wedging. I have the left-hand side is equal to 1/2 vi squared r to the s minus vi r to the s times vi. And the right-hand side is going to be equal to, just considering vi wedge, the second term there. Let me move the coefficient beta sub s out front. What I'll have is, 1/2 times that, vi squared times r minus vi r vi. Now, cancel out those 1/2s. Now I'm going to use a similar algebraic tricks that I used when I was solving for alpha sub s. I'm going to swap r to the s times vi around, making sure to add in the dagger. And we already see these vi squares coming in already. Those are just going to be 1, just to remind you. So let me rewrite the left-hand side as r to the s minus, this is going to be r to the s dagger times vi squared, which is just r to the s dagger. And the right-hand side is going to be equal to beta sub s, simply r minus, swap these two around, adding in the dagger, r dagger. So again, we see something very similar formally happening, where we have a rotor subtract away its conjugate on both left and right-hand sides. We've already dealt with this before on the right-hand side, so let me just remind you what that is. That's going to be 2 times beta sub s times sine of theta times b hat. Let's now work with the left-hand side. So I have r to the s minus its conjugate, or its dagger, r to the s. Let's go over here. That's e to the s theta b hat. Subtract away its conjugate, or its dagger. So again, that's going to be very similar to what we've worked with before. Instead of the argument in sine being theta, that's going to be actually s times theta. So the left-hand side is going to simply be 2 times sine of s theta times b hat. Again, I'm looking to solve for beta sub s. Let me cancel out the 2's. And again, equate those coefficients out front. So sine of s times theta is the same as beta sub s times sine theta, which means the formula for beta sub s is going to be sine of s theta divided by sine theta. So there you go. There's the coefficient that has to be in front of the final vector vf. So we have our two coefficients, the alpha sub s and the beta sub s. So we're done. So down here, now that we've got our two coefficients, the alpha sub s and the beta sub s, let's write out the formula for doing SLERP, the spherical interpolation. So v sub s, where again s is just some parameter, is going to be some linear combination of vi and of vf. So the coefficient out front of vi, the initial vector, is going to be sine of 1 minus s times theta divided by sine theta times the starting vector vi plus sine of s theta divided by sine theta times the final vector, the destination vector. So there you go. There's the formula given vi and vf to interpolate along the great circle on that sphere from vi over to vf, depending on the parameter s. So I've moved our SLERP formula up there to the top. So you might be wondering if you're doing some computations. So I'm given a VI and a VF, but this theta shows up here. And that's a last unknown that I might have to know if I were to doing some computations. So given VI and VF, how do you find the angle in between those two vectors? Now that's easy to do. Let me quickly show you how to do that. So remember that if I were to take the dot product of these two vectors, VI dot VF, this is equal to the length of VI times the length of VF times cosine of the angle in between them. Now remember, everything in sight is of unit length, so these two are actually 1. So it means that cosine theta is equal to the dot product of the two, which means that theta is just the cosine inverse of the dot product, VI dot VF. So pretty easy. So now you have everything you need to actually do a computation. You have theta is, you have your two inputs, VI and VF, and you have your parameter S, which you'll allow to range from not just 0 to 1. If you want to go beyond VF, extend further along that arc, or further along the arc in that direction, you have your parameter S. So you have everything you need to do a computation. Now, if you examine the arguments of the sine functions here, we have 1 minus s times theta over here. So we have a 1 minus s, but also an s times theta in the argument of this sine function here. So you might be thinking, well, you see a 1 minus s over here and an s over here. And that looks pretty similar to something that showed up just before in the linear interpolation formula. Remember, the coefficients were respectively 1 minus s times vi and s times vf. Now this actually makes good sense why you're seeing this sort of thing show up over here as well. Let me show you why. Suppose this angle theta between vi and vf is very small, which is to say that the initial vector and the final vector are very close together. They're not separated by that much of an angle. So in terms of a picture, that might look something like this. Let's say that's vi and vf. Perhaps looks something like this. So the angle is actually very small in between vi and vf. Now remember the small angle approximation of the sine function. When I have something like sine theta, if theta is almost 0, that is, it's very small, then sine theta is approximately equal to theta. That's the small angle approximation. Just to remind you, one reason why you can see that this is true. Remember what the Taylor expansion is of the sine function. That's equal to theta minus theta to the third over 3 factorial, and so on. You have higher order terms here. Now the small angle approximation just results from taking the first order term only, so that's why you just have the theta there as the small angle approximation. So let's use that small angle approximation here. And certainly if theta is small, then 1 minus s times theta is going to be small, and s times theta is going to be small too. Especially when you're in this range here in between vi and vf, you're interpolating in between those two. So let's use the small angle approximation here in this formula. So the numerator, sine times 1 minus s times theta, is just going to be 1 minus s times theta. In the denominator, we just have theta times vi plus, just using the approximation there, sine theta over theta times vf. Again, that's equal to v sub s. Notice the thetas cancel, and we're left with the formula for linear interpolation. So you can see, just going over here in the diagram, that does make some good sense why you're getting that, because spherical interpolation is almost the same thing as linear interpolation when the angle is very small. That is, this arc here is almost the same as the line joining the tips of the two vectors. So this makes good sense when you examine this formula and relate it back to what we've just learned about linear interpolation. So that brings me to the third and final topic for this video, which is normalized linear interpolation, or NLERP. So to explain what's going on in this procedure, let's go back to something that we've been talking about in both linear and spherical interpolation. We have an initial vector a VI and a destination vector, final vector, or VF, and you're interested in interpolating along those vectors in between, along some path. Linear interpolation, that path was along some line joining the tips of the two vectors. Spherical, it was along a segment of the great circle. Now, using that observation that when theta is pretty small, Lerp is almost the same thing as SLERP. We're going to talk about this now, the NLERP, Normalized Linear Interpolation. And you can see just by the name what it is linear interpolation, but just normalize the vectors that are being outputted in the interpolation procedure. Let me draw out what's going on here in the diagram. So if I have a VI and a VF, the path along which the interpolation is going to happen for Lerp is going to be along that line joining the tips of the two vectors, and the interpolate vectors would just be those vectors in between. And of course, too, if you were doing SLERP, it would be along some arc joining VI and VF along that great circle, of course. Now notice, again, when theta is pretty small, so this is theta. When theta is small, those paths are almost the same thing. Now remember, on this arc of the great circle, this is along the surface of a unit sphere. So notice that this linear path is inside the unit sphere. So these interpolate vectors coming out with Lerp are actually going to be a little bit smaller than length 1. They might be length 0.8, 0.9. So if you were doing linear interpolation, let's say you had some interpolated vector, let's say right there, V sub s. The way to bring this up to the surface of the unit sphere, that is, when you're doing the interpolation procedure, to not change the length of the vector, well, that's easy. Just divide by the length of this vector to make it of unit length. So that brings it up to the surface of the unit sphere. So VI and VF, again, those are of length 1. So to do normalized linear interpolation, just as the name says, you do linear interpolation, but normalize those vectors that come out in the interpolation procedure. So since normalized linear interpolation, what it is just doing a linear interpolation, then normalizing those vectors, dividing down by their magnitude to make them of unit length, the formula is not going to be too difficult. So let's return to our Lerp formula, the linear interpolation formula. So Lerp formula. So remember, that was just some linear combination of VI and a VF. And the right linear combination is, if you have V sub s, you have 1 minus s times VI plus s times VF. So if this is your Lerp vector, the NLERP, so let me call the vector that comes out of the NLERP, let me call that VS star. So that's your final vector, your truly final vector. This is just V sub s, where V sub s is just this stuff over here. Divide by its length. And this is guaranteed to be of unit length, which means the vector is going to reside on the surface of the unit sphere. And actually, you can see in this diagram here that all the NLERP is doing is just bringing these vectors that are linearly interpolated up to that geodesic path. So actually, the whole set of vectors that comes out of NLERP is really going to be the same in terms of that geodesic path as the SLERP vectors. Now, what are the differences, like if you're doing some sort of animation? So to see whether there are any differences, let's pick two vectors. Let me say that's VI. I'll pick a final vector which is relatively far away from VF. Let's say that's VF. So of course the linear interpolation is going to occur along that line, but the arc might look something like this. Of course, all these vectors which are linearly interpolated are going to be inside that arc. Now imagine you're allowing S to move over certain increments. Let's take this linear interpolation and divide it into 4 parts. So midway in between those two, that's going to be approximately there along the linearly interpolated path. So let me divide that up into 2, there and there. So this would be S equals 0.5, S equals 0.25, s equals 0.75. Now along the arc here, when you do NLERP, this vector from here to here is just going to be brought back up to the surface there. So let me draw that up, going up to the surface of that arc. So that might look something like this. Bringing this vector from here to here up to the surface of the arc, just drawing it through there. Might look something like this. I'm going to do the same for 0.75. Might look something like this. Now notice when we budget this out in regular intervals, the distance from here to here is shorter than the distance from here to here. And same thing over here. The distance from here to here is longer than the distance from here to here. So that means if you were doing some animation, if you were moving at 0.25 increments, because of those differences are different, you're going to actually change the speed. So if you were doing an animation, the vector would actually move faster in this region because it's going to have to cover a larger distance in the same amount of time. Or time here is it's the interval here, the 0.25 interval. So it's actually going to speed up as you do that animation if you're doing NLERP. Whereas if you're doing SLERP, if you're doing regular intervals along this geodesic, it moves at constant angular velocity. So I think that's all I had to say about those three procedures, the LERP, SLERP, and NLERP. Just from the abstract point of view, of course, if you have much more experience doing these in actual computation and actual practice, you're going to be much wiser than I am. But these are just some things we can learn from the abstract point of view and incorporating some of the tools from geometric algebra. So if you enjoyed this video, feel free to subscribe and stay tuned for more videos. Thank you for watching and take care.